Guys, this is starting to annoy me a little bit. If you're new to C programming and you Google something like linked list, then what you're going to get on the first page of Google is literally all just like int item, int data, int data. Even learnc.org is int val. And it's like, okay, storing integers in a linked list is cool if you're just trying to learn how a linked list works. But when you actually need to write a real program that works with real data, storing an integer is not actually that useful unless your specific use case is storing a file descriptor or something like that. Usually we want our data structures to be able to link to more complex data types. And so how do we do that in something like C, where it's all kind of very strict on us? The solution to this is a void pointer, and you'll notice that the C standard library actually uses void pointers everywhere in order to give us a type agnostic API. So what we're going to do is essentially use this technique ourselves on our own personal libraries and data structures that we want to build. To demo this technique to you, I've got two elementary data structures. The first one is a linked list. Now let's look at our implementation versus the ones from Google. You'll notice that the data type that I've specified in my linked list node is not an integer, it's a void pointer. And what I've actually got down here is a struct that represents the state of the linked list itself. Why do we need a state struct all of a sudden? Well, here's the trick. What you need to think about when you're designing a type agnostic library, you need to know everything you can about that unknown data type except for the type itself, because that's the thing that the compiler is going to bite you on. So in terms of a data structure, what we need to do is we need to know the size of the data, and that's what we collect here in the metadata for this struct. So the user of the API can provide the size of the data. And this is common across other functions, like if you use memcopy and stuff like that, they all need to know the size of the data that they're operating on, but they don't necessarily care about the data itself. Now, with a linked list, it gets a little bit more interesting because sometimes we do want to care about the data itself. For example, how are we going to walk our linked list and search for a value? Well, that's where the magic of function pointers comes in, where you pair it with a void pointer. And this is a technique that's used, for example, in the C standard library binary search implementation, which is where you simply provide a compare or matching function, which is user specified. So when you initialize this linked list, the user can provide a matching function that takes in data structure 1, data structure 2, and compares the two to see if they match. So for example, if you define a struct, and I've got one over here. So what we're going to be testing this linked list with is my wicked data structure. And my wicked data structure has a key and a value. And I've got two examples of match functions here that we could give to our linked list search. The first one is just based on the key comparison, which is the integer. And so, for example, what you do with the wicked match is you take in your void pointers, because obviously that's what we need to do, and you cast that to your proper data structure type. And once you've casted it, you can actually access the struct members. And that is the trick that lets the compiler be happy with you. It's essentially like at compile time, everything that needs to use that data still knows what the type is because you do the cast. And to be fair, you do rely on the user to be accurate with their APIs and their initialization and everything. But the data structure library does not care about the underlying data because it never has to use it. What it's going to do is reach out to a user-specified function which does know what the type is. And that's kind of the whole trick here. And so when you come across complete vibe-coded slop, like the zero lang repository from Vercel Labs, which has a lot of C that I've had a little bit of a look through, and you come across something like this, which is where they've got a function vec type and a shape vec type, which are identical except the pointer that it stores, you can know that there is a much better way to do that if you weren't completely vibe coding it using AI. 4.1k GitHub stars, by the way. Now, how does our library actually work with the void pointers? It's cool that we can write that in our node over here, but when it comes time to actually insert that into our linked list, how does that actually work? We come over here to this ll insert function, and the first thing we're going to do is alloc the node container, which is this whole container here. And then if you come over to this section, this is where we actually work with it. I've got an option here, which is BYOM, that's bring your own memory. So when we're writing a data structure like this, typically I like to code for two scenarios. The first scenario is where the calling function or the caller is going to own the memory that that element is stored in, and we're just going to copy a reference to that. And so what this allows the caller to do is hold that struct in a buffer somewhere if you want to pre-allocate all of this memory. and simply pass the pointer to that, and the pointer is what's stored here. And so it's the caller's responsibility to clean that memory up. You can also do basically a copy container, which is where you malloc the size of the data, and you simply memcopy that data in. And because memcopy is working with void pointers, and we don't actually care what the underlying data is, it's just all bytes, and I've done a video on how everything is just bytes that you can check out as well, this works perfectly fine, and we never have to inspect the type of the data that's being passed in. Now for a little demo about how this is going to work. So what you can see here is I've got my wicked data structure, and basically what I'm going to do is just loop through to 25 and insert 25 of them. It's got a key, it's got a value. The key is simply going to be I, which is the index of the loop, and the value is going to be %dist1. And so we're going to use ll insert, and then we're going to search with the int compare. So the int compare is this first one here where it just checks the value of the key. And then what I'm actually going to do is change the matching function in the middle of the program to wicked match string, which is going to search the values with strcomp. And what we're going to do is essentially use our search term as %dist1. And we're going to see if our generic linked list data structure can handle this. So if I compile and run this, what you'll notice is that our search with both of these does in fact work perfectly, because our matching function is the thing that actually links the underlying data to the comparison, and the linked list data structure is just a helper that can run whatever function we want. We could make it hardcode is key equal to 0, and it would work the exact same way and just match all the zeros. It's that simple. One warning I want to give you about using function pointers though is that the linker doesn't know how to optimize them, because obviously you don't know what that function is going to be at compile time. And so if you're writing very highly performance critical code that is operating on a very specific set of data in a very specific type, it's often better to just hard code that into your implementation if it's just a one-off thing for that specific data type and it's in a very high performance application. And when you know how to do something like this technique, it's easy to fall into empire building, which is where you build unnecessary abstractions where you actually don't need to. The point of what I'm trying to show you here is how you as a C programmer who's trying to advance can build up over time your own library set of useful data types, functions, helpers, anything. And if you want to be able to do that and use them in your projects, you've got to be able to work with arbitrary data. But be aware of performance if every cycle counts. To demonstrate that I'm not a one-trick pony and that this technique is generalizable, here's a ring buffer implementation. Now, this is still fairly simple. It's about 140 lines of code. And if you come over here to the state struct, you'll notice a couple of familiar things from our linked list. We've got the data size for the metadata. We've got a matching function over here, but we've baked in some ring buffer specifics. So for example, n is the total length of our ring buffer, like how many elements can it store. Len is how many elements are currently in our ring buffer. Head and tail obviously represent the head and tail of the ring buffer. Expandable, now this is whether or not we are managing the memory internally or if the caller is going to manage memory, and I'll show you how that technique is working in just a second. And we've got a backing buffer that's going to store the objects in our ring buffer. And so if we come to ring buffer init, you'll notice a fairly similar API to the linked list. You pass in the ring buffer object, you pass in the data size. You're going to have to initialize the ring buffer with a total length at the start. You give it the matching function, just like the linked list, and you give it a backing buffer. Now, the backing buffer, as I said, is going to determine if this is A, expandable, and B, if we're managing it ourselves, or if, for example, in the caller has defined a big buffer that represents the structs. So, you know, like struct, my struct, and then like 100 of them. If it's externally managed, then we simply set the backing buffer to the one that's specified. And if it's not, then we're going to allow it to expand and we're going to malloc that size ourselves in terms of the data size times the length. Now you may be wondering, how can we put stuff on the ring buffer and pull stuff off if we don't actually know what the data is? And this is what I was telling you about before. We simply only need to know the size of the data. And so what we can do here with, for example, ring buffer pull is we can use pointer arithmetic in order to find the position of that in our byte buffer that is backing this ring buffer. So you can think of in memory, we have this big buffer of bytes where it's all allocated, where each individual position is going to be the size of the element we specify in dsize. but by having it be a byte buffer, it's generalizable to any piece of memory. But we're still going to do operations in terms of the size of those individual elements. And if you do it in that way, you don't necessarily need to know what the type is, you just need to know how big it is so you know which offset to point to. And that's exactly what we do here. So when we go and pull things off, when we pull things from a ring buffer, we want to start with the element that's at the head. And so what we allow the user to do is pass in a container to put that into, and we simply find the position in our ring buffer using the backing buffer start plus the head times the D size. And so that is going to track the exact position in our byte buffer where that object is without having to know what the object actually is as its type. And if the caller has specified a container, we can populate that container with the contents of this using, again, our friend memcopy. And like I said, memcopy, we don't need to know what the type is, we just need to know the position and the size, which we already have because that's part of our metadata. And that way, we can simply give the data back to the user. They know how to deal with that because they can do a cast on their end, and our ring buffer operation is done. We have a very similar thing on the push side of things, where we do a pointer arithmetic to get where the tail position is. We memcopy to that position in the backing buffer, and then we go off from this and we loop the tail around if it's 0, because a ring buffer, it goes around, things like that. And I've got some other code in here to expand, just to show you about expansion. So if our ring buffer gets full, we can expand that like this. I'm not going to get into the nitty gritty because this is not a tutorial on ring buffers, it's a tutorial on void pointers, but you get the idea. You can double the size of the buffer when it gets full. One last part of the implementation I want to go over before I can demo this ring buffer to you, and that's this rbpop search. And this is purely here so that I can show you a generalization of the matching function pointer technique. Basically what this is going to do is it's going to go through everything in the ring buffer, and if it matches based on the matching function that the user has specified, it's going to pop that, and then it's going to stitch the ring buffer back together. And so what you can see here is that once we found one, we're just going to do a cheeky little goto, which mem copies this into the container that the user has specified. Note that we don't allow a null container. And then it's going to simply stitch the ring buffer back up, depending on what the layout of the ring buffer is. So if you think about a ring buffer, when head is less than tail, it's very easy to stitch up. You just remove one from the middle and move them all. But when the wraparound case, it gets a little bit more complicated. And so that's what we're dealing with here. I'm not going to get into the details, but just that's kind of the idea. Now for the ring buffer demo, we are going to be pushing and pulling myWicked data structure, which if you need a refresher, myWicked data structure simply consists of an integer that makes up the key and a value, which is a string of 64 length. And we've got two matching functions to play with. One matches based on the key and the other matches based on the string compare of the value. So if we come down to the RB demo over here, what I've got for you is an init function that uses wicked match, which is the integer comparison, and I'm going to insert 25 of these, where w.key is equal to I, which is the loop iterator, and w.value is equal to our %dist1 string. Now, what we're going to do after that is I'm going to take 5 integers that are randomly generated, and I'm going to try and pop search them out of RB so you can see that matching function in action. And then after that, we're just going to pull the rest. So let's compile and see if this works. And you can see here, we pop 3, 11, 6. We couldn't find 6 because I guess it chose 6 again. Obviously, that makes sense. I don't know what the chances of that are, by the way. Like, what are the chances, if someone can do the maths, what are the chances of pulling the same value in this random 5 thing? But anyway, then we try and pop 2, and as you can see here, it pops them correctly, like key is 3 and values the first one, the 11th one, the 2ndest one, and what we're going to do if we pull the rest of these, you'll notice that we don't have a second one, we don't have a third one, we don't have an 11th one, and so on and so forth. So what you can see here is that our ring buffer is actually working. And once we do the rpop search to show you the container, by the way, what we have is a myWicked data structure up here defined as w, and we simply pass w in as the container that our ring buffer structure is going to copy into. And then after that, you can see we can just access the results like normal. I really hope you guys enjoy this video because yeah, like I said, I got a bit annoyed. Like if you just Google tutorials for how to make data structures in C, every example uses just an int or something, or like a string or something. It never shows you how to do generic libraries that you could actually use for anything you want. And that's what I wanted to do in this video. So please let me know if you found it interesting. Thanks.